In this video, I want to talk about writing quadratic functions given two complex roots. So remember, to be quadratic, it needs to be degree 2, and the complex roots will come in conjugate pairs as long as the quadratic function has real numbered coefficients, which we're going to go ahead and say yes. Alright, so in this first example, we have x equals plus or minus 5i. So I have two roots here, a positive 5i and a negative 5i. And remember, I can write any quadratic in factored form, x minus a times quantity x minus b. So the a and the b are just going to be these roots. So let's go ahead and plug it in and see what it looks like. So f of x equals x minus a. So we'll use 5i for the first one, and x minus negative 5i for the second one. So when we subtract a negative, we know that's just going to become a plus. So our function here is actually x minus 5i and x plus 5i, which when we go through and multiply this, these are complex conjugates. So I just need to multiply the first to get x squared, and then the last to get negative 25i squared. But of course, our I squared is a negative 1, so that will change that subtraction sign to an addition sign. So our quadratic function in standard form will be x squared plus 25, and this will be the quadratic function whose roots are plus or minus 5i. In our second example, our quadratic function that we're going to create will have two roots, and they're both complex again, negative 2 plus 7i and negative 2 minus 7i. Alright, so we can put them in this form where we have the factored form with the roots, so a and b are the roots. So our quadratic function f of x will equal x minus the first one, so we can say negative 2 plus 7i, and then x minus the second root, which is negative 2 minus 7i. And then we have a little bit of simplification we can do inside here. So f of x equals x plus 2 minus 7i and x plus 2 plus 7i. All right. So as we saw in the previous example, our multiplication ended up being the difference of squares, or we were multiplying together two complex conjugates. Well, we can see it or visualize it the same exact way, even though there are three terms. So this x plus 2 could be our first, and so x plus 2 and x plus 2, and then our 7i and 7i. But here's the subtraction, and here's the addition. So we could say this is a minus b and a plus b. And in that respect, multiplication here will be much simpler. So let me show you what you need to do. So when we're multiplying difference of squares, we need to square the first, so x plus 2 squared, and then we're going to multiply the seconds here. So negative 7i times positive 7i will be negative 49i squared. Now, simplifying it from here will give you x squared plus 4x plus 4, and that's this binomial squared. And this I squared is negative 1, so it'll change the subtraction to an addition, so 49. So our quadratic function will end up being f of x equals x squared plus 4x plus 53. And this quadratic function that we just created will have these two complex roots, negative 2 plus 7i and negative 2 minus 7i. But I do want to go back real quick and just say another word about this. So let me rewrite this and show you kind of how we did that and why we didn't do it another way. Alright, so typically when you have three terms and you're multiplying by three other terms, it's going to be a lot of distributions. In fact, you're going to have 9 multiplications, and then you got to go hunt for some like terms. So we always like to make things as simple as we can. So instead of doing 9 multiplications, many of which will end up canceling out anyway, we were able to visualize this in a larger scheme. So x plus 2, and then 7i, and then of course 1 was minus, 1 was plus, and that's kind of what we were talking about. A minus b times a plus b. And that's why we were able to not worry about a lot of these multiplications, is because it was just difference of squares anyway. In this third and final example, we're going to use a little more difficult complex roots. We're going to use 5/3 plus 1/6 and 5/3 minus 1/6. And we once again would like to write a quadratic function that has these complex roots. And so again, we're going to start the same exact way, x minus our first root times the quantity x minus our second root. Let's go ahead and set that up. F of x equals, so it's going to be x minus 5/3 plus 1/6, and then x minus 5/3 minus 1/6. Okay, so same as before, we're going to go through and simplify some stuff. So x minus 5/3 minus 1/6 and x minus 5/3 plus 1/6. And once again, we can use this difference of squares factorization. So the x minus 5/3 is our a. 1 is negative, 1 is positive. And then this 1/6 will be our b. So we have f of x equals x minus 5/3 quantity squared, and then minus 1/36 I squared. Well, all right, so the I squared is a -1, so that'll change that to a positive. Whenever we do the perfect square formula for this guy, we'll have x squared minus, and it looks like 10/3 x plus the square 25/9, and then plus 1/36. So our constants can go together, and we'll have x squared minus 10/3 x. Getting common denominators, we'll multiply the top by 4 and the bottom by 4. So the 9 times 4 makes the common denominator of 36, and the 25 times 4 gives us 100 plus 1, so 101 over 36. I am going to make one little kind of tweak right here. I don't like having these fractions here and here, so I'm going to go ahead and take my whole function and multiply it by 36, which is the common denominator between 3 and 36. Remember, because the only goal of this problem is to write a quadratic function with these roots. So I can actually run through and multiply by a constant, or I can, it's called scalar multiplication also. I can scale this quadratic function by multiplying by a whole number, and it won't change any of its roots, but it will help get rid of these fractions and make it look a little nicer. So f of x, which is my final function, ends up being 36x squared minus 120x plus 101. So right here will be our really nice quadratic function that if you were to solve that, you would get these two complex roots.